Okay, I gotta shut off the music there so we can get this going. So, yesterday we did great on the lab. One of the students stayed after and wanted to work on problems, and so we did. And it got me thinking that problems 3 and 4, it might be useful if I were to go through and do a video and help you guys know exactly what to do in the steps that we do. So here we go. I've got problem 3 kind of laid out here. The numbers don't really matter until the end, so we'll come back to M1, M2, and the acceleration A. There's only one direction for our acceleration to go, and that's this way. The driving force is going to be gravity. So on M2. So I'm going to make that positive. So I'm going to just say positive here, positive up there. And over on M2, I'm going to say that down is positive and up is negative. So then we can do some stuff, okay? And you can't look at both of these objects at the same time. You have to do them independently. So over on this side, I'm going to do M1. And then over on this side, I'm going to do M2. And then we're going to get our equations, and then we're going to combine them. And you'll see how it'll be kind of nice when we do combine them. All right, so I want to do M2 first. So we're going to look at the sum of the forces. It doesn't really matter what direction it's going in. We can call it Y, we can call it X, we can call it whatever we want. So I'm just going to leave it not anything, because really we're only traveling in one dimension. So that's fine. So we've got our sum of the forces is going to equal M2 times the acceleration. And we've got to have our free body diagram. So here's M2 free body diagram. What are we looking at? We're looking at this direction is M2 times G, and in this direction we've got our tension. So we can say tension is going in the negative direction. So I'm going to say M2G minus T. And so this is our first equation. So I'm going to call it equation 1. Put a little 1 there. And now we can come over here and do M1. So M1 actually has, let's do the free body diagram for M1. We have a normal force. We have M1G. We're going to have a frictional force, and it's going to point in the opposite direction of the movement, and we already just laid down what our movement is going to be, and then we have a tension that's pulling on our little guy. So that's pretty nice, and we can do a similar thing, but as far as coordinates, but I already laid them out, so those are our coordinates there, and we're just going to do a sum of the forces. Now this time I'm going to say this is the sum of the forces in the y direction, because our mass of 1, we're only dealing with M1 now. Our mass of 1 is multiplied by AY, but we know that AY is equal to 0, so we're going to say that that equals 0, and then we're going to have our Fn going up and Mg going down. So anytime you have something like this, you know that those two things must be equal. So we can say that Fn equals mg. And there's one other little trick here. Our force of friction is equal to our mu times our normal force, and so I'm just going to say mu m1 g. I gotta keep my ones in here. Okay. So that's fine and good. Now let's do our sum of the forces in the x direction. So we've got m1 times ax, but I'm not going to call it ax because it's the same a that the other m2 is doing, because the rope doesn't stretch or shrink or anything. So the two a's are the same. I can write that. A for 1 is equal to a for 2, which just equals a. So I'm just going to leave that as a in the x direction. And that, now all we have to do is do our force thing. We've got T pulling to the right, that's a positive. And we've got our friction force pulling to the left, that's a negative. So I'm going to write the force of friction, m1g, like this, because that's what it is. And those are the things that we know, or we don't quite know mu yet, but we're going to solve for it. So that's my second equation. All right. Okay. So now I have two equations. We don't know what mu is. We're asked for mu. In fact, let's talk about what we're asked for here. I'm going to slide up just a little bit. The question is, what is mu static minus mu kinetic? You might want to ask yourself first, which one of these things is larger than the other, and hopefully you guys come to the conclusion that mu static is larger than mu kinetic, and so therefore mu static minus mu kinetic is going to be positive. So that's greater than 0. Okay. So we're going to need mu. We also don't know what our tension value is, right? Over here too, in equation 1, we don't know what the tension is. So what do? We can take equation 1, and if equation 1 has minus t in it, and equation 2 has plus t in it, if we add those two equations together, so we're going to do 1 plus 2, I'll write it out here, m2a equals m2g minus t, and then we're going to add to that m1a equals t minus mu m1g. And we're going to add those two things together. So here we go. m2a plus m1a on that side. On this side, we've got m2g minus t plus t minus mu m1g. And now we've got our plus t and minus t. That just goes to nothing. And we can rewrite that as m2g minus mu m1g. Okay. Those are, it's a good place to start working. Let's get back to our thing. The actual question. Okay, that's our question. What does that mean? That means we want to solve for mu. This term is negative. So I'm going to move it to the other side of the equation, and I'm going to say mu m1g is equal to, then I've got m2g here, and yeah, good. All right. I was seeing something and I'm like, oh boy, I don't know about that. I need to move this to the other side of the equation with the m2g. So I'm going to do that. I have to make it negative. So I'm going to say m1a minus m2a. And now we can go through and do our thing. Divide out m1g. So mu is equal to m2g over m1g. And then we're going to subtract off a times m1 plus m2. You guys play around with the algebra. Make sure you know how I just did what I just did. And I'm going to write g there and m1 here. Okay? I'm doing it so that these two guys are, because they have the same units, accelerations. And so I'm going to keep those two guys together. And I'm also keeping the masses together, which kind of makes things nice. Now, we want to have mu static. So let's look at what happens when mu is static, and we want to have mu kinetic. All right. So when mu static, what is A? Well, it's static. There is no acceleration. So A has to be 0. For mu kinetic, A can be whatever we want. A is greater than 0, let's just say. All right? So when we say we want to subtract mu s or mu k from mu s, then we just use this same mu equation, only in the mu static situation, for mu static, A equals 0. So I'm going to write m2, I'm going to cancel out the g's. Okay, those g's are going to cancel. So I've got m2 over m1. And now I have minus all this stuff multiplied by A. Well, anything you multiply by 0 is 0, so it's 0. So really, mu static is equal to m2 over m1. All right, now let's do mu kinetic. Mu kinetic is equal to m2 over m1. But now we're going to subtract. We've got our A over G, and we've got our m1 plus m2 over m1. So I think now it's pretty simple. When we take mu static and subtract mu kinetic, we're going to have a nice simple thing. We're saying mu static minus mu kinetic. We've got m2 over m1. We're going to subtract mu kinetic, so that means I'm subtracting m2 over m1. So this is obviously 0. And minus a minus is a plus, so I've got plus ag times A over G times m1 plus m2 over m1. All right. That leaves us with just this. And now we can go back to our numbers. What were our numbers? Well, let's plug them in. My numbers, I don't know what your numbers are, but my numbers have A equal to 1.421 meters per second squared. My M1 was equal to 5.31 kilograms. My M2 is equal to 2.389 kilograms. And we just take all those things and shove them in there and do our plug in chug. Be a good name for a Quickie Mart. Okay. So, what does that do for us? In my case, I'm not gonna, you can plug in those numbers. I'm not gonna do it for you over again. You can plug in those numbers. I'm gonna write down what I get when I do that. 0.2102. Now I want you to know mu is what? Unitless. And you can also see that it's unitless because acceleration over acceleration, mass over mass, has to be unitless. So we're unitless, and this is my answer for problem number 3. Okay. Problem number 4. Problem number 4, not quite as easy. It's got some things that we need to deal with. Okay, so I have a little ruler here. We can see if this is going to help me keep things straight. Maybe it will. Oh boy, look at all that. Nice. It's because of my pad here is it's hard to work with a little bit. Oh, I don't want that. I want this. Yes, please. That worked well. All right. Sure. Okay, so there's theta. We've got, we'll call this one M1. It's connected. There's a pulley. And we've got a mass 2 here. And it can be also variable. All right, so this is variable. And we're going to actually do a few things with this one. The first thing is, let me get my notes here, hold on. What is the maximum value that M2 can be so that the whole thing stays still? All right, so what we need is 2 free body diagrams, and I'll write A. What is M2 such that, oh, nice work, such that A equals 0. And I should say M2 max, right? Because the more we put into M2, the faster it's going to pull M1, right? But we still want A equals 0. So we don't want to give it too much. We want to make sure that the friction still holds it, okay? And we're given stuff. We're given mass 1. We're given theta. We're given mu static because we're keeping it still. This means static. And M2 varies, and that's what we're trying to figure out. What is M2 such that that happens, okay? All right, so we're going to do the same thing that we did before. We're going to do M2 first. We're going to do our free body diagram. And I'm going to say for this one, down is positive. So I'm going to draw M2G going down. We've got our tension going up. Tension M2G. Okay, so that's our free body diagram. We can then do our sum of the forces. And going to be 0 because we're not moving. So that means that if I say that down is positive, because that's the direction that acceleration is going to happen, up is negative, down is positive, M2G positive, minus T negative. I don't know if I want to do it like that. I don't want to do it like that. I'm sorry. I want to keep my MA. I want to keep my M2A. M2A. I want to keep it because I want to solve, we're going to have this as our equation 2. We're going to have another one, equation 1, and the equation 1 and equation 2 are going to add together just like before and cancel out our t. So we're going to keep the a around. Even though it's 0, we're going to keep it around for a little bit, okay? Okay. We'll substitute in 0 later, in other words. All right, so let's do our free body diagram for M1. We've got our slant here. We've got our tension pulling up. We've got our force of friction pulling down. We've got mg, m1g going that direction. Here's theta. So that means that mg, m1g sine theta is pointing in this direction. M1g cosine theta is pointing in that direction, and there's my normal force. Okay, now in order to do this properly, of course, we want to do our sum of the forces in the y direction. You do the y first. Our acceleration in the y is not the same as the acceleration in the x that we're dealing with here, okay? Our acceleration in the y is also equal to 0, and we're going to substitute 0 in right away. So we're going to say that this gives our sum of the forces in the y direction equals 0, and then we're going to say Fn is positive. In fact, let me do my coordinates. I'm going to say this is positive and this is positive, because we know that our acceleration, if we had any, was going to go this direction. That's why my force of friction is pointing down. Okay, so y direction, Fn positive, m1g cosine theta negative. So let's rewrite that as Fn equals m1g cosine theta. Make the one a little bigger. And hopefully you guys remember this. F, force of friction, is equal to mu times our normal force. So we can then say that our force of friction is equal to mu m1 g cosine theta. And we can do our sum of the forces in the x direction now. m1a, because ax equals a, right? They're both accelerating at the same. The string doesn't stretch or any of that stuff, so they're both accelerating the same. M1a is equal to t, going positive. I've got the force of friction going down, backwards, so I'm going to write minus mu m1g cosine of theta. And then I also have, going in the opposite direction, m1g sine theta. Okay, so this is in the x direction, this is in the x direction, and this is in the x direction. This is in the y direction, that's in the y direction. All right, that's my second, or my, what I'm going to call equation 1. I'm doing it because I'm dealing with m1 here, so that's why this is equation 1. I'm dealing with m2 over here, that's why this is equation 2. And we're gonna, I don't want to get rid of equation 2. So let's rewrite those. We're gonna add 1 to 2. 1 plus 2. We'll do it just like we did before. We've got m1a equals t minus mu m1g cosine theta minus m1g sine theta. And we're going to add m2a equals m2g minus t. So that's this. And we're going to add those two things together. So on this side we get m1 m1a, I don't know if I want to, I can't remember if I want to break those up or not yet. Yeah, I don't think I do. I want to keep them separate. Okay. Keep the terms separate. So I've got m1a plus m2a on the left side of my equation sign. It's clear that this positive t and this negative t are going to disappear. They're going to go away. So I'm left with m2g minus mu m1g cosine theta minus m1g sine theta. All of that is true, okay? So this is like our main equation. This is the main thing. We're going to use that, all right? Okay, so that's our main equation. Oh, trying to push up without pushing up. Now, what is our question again? Well, what is M2 in this situation where A is equal to 0? Well, if A equals 0, these guys are going to go away. So I'm left with 0 on one side, m2g minus mu m1g cosine theta minus m1g sine theta. And I really want to solve for m2. So I can do that. I can just put m2g on one side and put the others on the other side. I'm going to do a little math because I don't like plugging in. I don't like plugging in numbers when I really don't need to. The g's for every term cancel. So now I can say that m2 is equal to, and I'm going to factor out m1 here. And now I have mu cosine theta plus sine theta. Nice. What is that number? So we can now go back in and look at or talk about what those numbers are, because we're going to plug and chug, right? So M1 is equal to 126 kilograms. Theta is equal to 48 degrees. I've got mu static is equal to 0.42, and that's the mu that is going to go right in here, okay, because we're maintaining static situation, and we're solving for M2. So I'm going to write M2 is the thing that we are questioning. What in the heck is M2? Of course, you know G and all that other stuff. So we're going to leave that out, but it's not even in our equation, so fine. So M2, if you take these numbers and throw them in there, you're going to get, what do we get? Where my number at? M2 equals 129.0 kilograms. So hopefully that's what you got there. Okay, now B. I'm going to scroll up a little bit. B is kind of similar, but B wants to know the minimum. Minimum M2 so that M1 doesn't slide this way. So there's M2. And we want to make sure that M1 doesn't slide back down that way. Well, if it's sliding that way, then our force of friction is going in the same direction as the tension force. So I'm going to go back up and grab the equation that we started with, but I'm going to take everything that has friction involved with it, this main equation. This main equation, here's where the friction comes in, and I'm just going to make this positive. Okay, so that's now my new main equation because I've flipped around the friction for the situation. You can go back through and do all the whatever rigmarole work that you might want to do to figure that out. But if you do, you're going to come up with M2G equals M1G sine theta minus mu M1G cosine theta. Again, we can cross these guys out. We can factor out M1 on one side. So we've got M2 is equal to M1 times sine of theta minus mu cosine theta. Okay. Fine. Right, fine, good. My M1, 126, I'll write them out for you guys. Sine of 48 degrees we're going to subtract off 0.42 times cosine of 48 degrees. And lo and below, I know that's not how the saying goes. I had a French instructor one time who used lo and below instead of lo and behold, and we cracked up. Okay. What is that number? We are hitting that number. That is 58.2. 58.2. Okay. So 58.2 kilograms in my scenario. So that's B. Now we can go to C. And the C question is if we're given a mu kinetic, so we've got mu kinetic is equal to 0.31, and M2 is equal to 158.7, then what is A? All right, well, you guys know I don't like having a negative A, right? If you do all your work and you get a negative A, then that just means it's pointing in the other direction. So which direction is our acceleration happening? Well, our old case, 126 was M2, right? Or I'm sorry, M1. That was our old case. And when we did the sliding backward this direction A, when we did that, we found that M2 had to be greater than this. I'm sorry. M2 had to be greater than that, so that means M2 is a minimum at that point. Greater than or equal to, we could say minimum. Okay, but if we come back up here, if we're sliding in this direction, A, then our M2 maximum is 129. But look here, they give us an M2 of 158. And not only that, they've decreased our mu static to a mu kinetic of this. So if you have more M2 mass and less friction, you're going to spin this direction. This pulley is going to go in that direction, and M2 is going to pull the whole system in that direction. So I am going to erase this A. That is not the A we're going to do. We're doing this A. So that means we have to go back up to our original equation. Okay, and instead of making this negative, we're going to make it positive. What did I do? I made it positive before, now I'm making it negative. We're adding them together. This one needs to be negative. Yeah. Okay. So I'm making that negative, pointing down the slope instead of up the slope. That's our force of friction. So great. We've got all of those things, but what are we doing? We are solving that whole thing. What is A? So the question is, what is A? So let's get that equation. And we're gonna solve this main equation for A. All right. So M1 plus M2 times A is on the left side. m1 plus m2 times a is on the left side. That's going to equal... I'm trying to drive too fast. That's going to equal m2g minus mu m1g cosine theta minus m1g sine theta. So m2g minus mu m1g cosine theta minus m1g sine theta. And I need to solve for a. If you notice, we can factor out g on the other side, so I'm going to factor out g. I'm left with g times m2 minus mu m1 cosine theta minus m1 sine theta, and all of that over this that I'm dividing out. m1 plus m2. Okay. Let me check my notes, make sure I've done this thing for you guys correctly. Mu, m1, m2, and they're giving us mu, and it's a mu kinetic, so I'm going to put a little k there, and that all seems right. So we're going to, again, plug and chug. Plug and chug. Some Mountain Dew from 7-Eleven. Okay. Here we go. I'm not plugging in any. I'm not going to. You guys can do this. You know all the numbers. We talked about it. You can go back and get them. However you want to do it, you're going to end up with 1.3399 meters per second squared, but this is essentially a 4. Can't get closer really to 4 than that, so a little bit closer. I guess we can throw another 9 on there, but let's just say that A is equal to 1.34 meters per second squared, and that ought to do the trick. Okay, so this is for homework 8. I'm going to post this, and good luck on it, guys. Thank you.